All right, we are continuing on with the 6.3 notes, and we're now going to be looking at our inverse trig functions again. We're going to have integrals that result in inverse trig functions. We are not doing the integrals of inverse trig functions. We're going to do integrals that result in answers of inverse trig functions. Basically, we're just going to be undoing the answers we got from the derivatives and resulting back in our inverse trig functions. A couple things I just want to point out. Like before, the most important formulas will be the integrals that result in answers with inverse sine and inverse tangent, the inverse cosine and inverse cotangent integrals that involve those inverse functions will be identical with just a sign change. Okay, so you could easily derive them. Less likely to see the integrals that result in inverse secant or inverse cosecant. But these two in particular, you really need to make sure and know. Something else I just want to point out on this formula is that the one involving inverse tangent has a surprising 1 over a in the front here as a multiplier. You're going to really want to watch for that if you see something that looks like that form. So what I'm going to look for, if I'm looking at number 5, this looks like inverse sine. This looks like inverse sine. Notice that on the denominator I have the square root of a constant minus an expression squared. That's what I'm looking for. By the way, it must have that minus. So in this particular situation, u is going to be the square root of the function that's being squared, which in this case is just x. A is going to be the square root of the constant that's before the minus sign. Must be the square root. I know in this case it looks the same. Now this -5 in the front is just a multiplier. What I tend to do is I tend to really quickly rewrite this. Now first of all, we are going to think about u substitution. I'm going to rewrite this all in terms of a and u. Where it said dx, I'm going to replace it with du. I've already pulled the -5 out front. That's now 1. And I'm going to then just replace this with the square root of a squared minus u squared. This is something that I do just to verify that I'm not forgetting anything in the process. I'm not leaving out a term or missing something. So then this matches the inverse sine. So this would be -5 times the inverse sine of u over a plus c. U is x and a is 1, so that will just be the inverse sine of x. -5 times the inverse sine of x plus c. Number 3 is also a problem. That is inverse sine. Notice the square root of a number squared minus a function squared. U is going to be the square root of the function that's being squared after the minus sign. A is the square root of the constant. This 3 I'm just going to pull out front. Now, I do need to think about u substitution. I'm going to rewrite this all in terms of a and u. du is equal to twice dx. I don't have a 2 over here, so I'm going to divide out that 2. So I can replace this dx with 1/2 du. And then here I would have, I already pulled the 3 out front, 1 over the square root of a squared minus u squared. This is a match for my inverse sine formula, so 3/2 times the inverse sine of, it's always going to be the same. It's always going to be u over a for all of these formulas. So u, which is 2x, over a, which is 1, plus c. I could just write that as 2x if I want. Number 3, this is a match for inverse tangent. The integral resulting in inverse tangent on the denominator would have a constant squared plus some function squared. So I guess I could label a first. I don't know, you might like that better since it comes first in the formula. I should have done that before, sorry. A is the square root of the constant. U is the square root of the function being squared after the minus sign. You do want to do u substitution, or at least think about what it would do. In this instance, there's no changing of the constants. So this could be replaced by the integral of 1 over a squared plus u squared, and dx can be replaced with du. I'm just doing this to make sure I've not missed anything, such as maybe how constants might change in u substitution. So then this would be 1 over a times the inverse tangent of u over a plus c. The 1 over a that I'm writing down here is part of the formula for this integral. I have it here in green. So a is 2, so this would be 1/2 times the inverse tangent of u, which is x minus 1, over a, which is 2 plus c. Now, you might not need to write down as much as I'm writing down. To be honest, once you get comfortable with these, you can do a lot of this in your head. So I'm showing more steps perhaps than you would choose to. That's up to you. All right, this one, maybe this kind of looks like potentially resulting in inverse tangent. I'm a little curious about that t on the numerator because all of my formulas don't have that on the numerator. They just have du, which would kind of be like a 1 or a constant. But let me just start the process and see what happens. So a would be the square root of the constant, which is 4. U would be the square root of the function that's being added on, which would be 2t squared. U substitution is still required. Du is 2t dt. I'm starting to see where this t dt is going to play out. I don't want the 2 here. So I'm going to go ahead and just isolate t dt. And t dt could be replaced with 1/2 du. Please notice I'm still writing the integral symbol. I've not integrated yet. I'm just going to rewrite this all in terms of a and u and make sure that I've not skipped anything. On the numerator, this would be a 1 over, or du over if you'd rather, a squared plus u squared. This is a match for inverse tangent. Now this 1/2 is still out front. It's a constant multiplier. And then I would have 1 over a times the inverse tangent of u over a plus c. And as the last step, I'm just going to replace. A is 4. U is t squared. And a is 4. So I guess I should simplify out front. 1/2 times 1/4 is 1/8. It's very common for people to put 1/2 instead of 1/8 because they forget that the inverse tangent formula has the u over a as part of the formula. All right, example 9. This one looks like the integral resulting in inverse sine. You might notice that it's a definite integral. We can still do this. A would be equal to the square root of the constant, that's before the minus. U is equal to the square root of the function after the minus. Du is equal to dx. I'm going to do a quick rewrite. I'm going to replace dx with du. You can put that on the numerator. I tend to like it on the side. It's up to you. And this would be 1 over the square root of a squared minus u squared. That's a match for our formula that would result in inverse sine. Now, I should think about the limits. The limits would need to change to match my u substitution. However, u and x are the same. So in this particular instance, they don't change, but you should always consider if they would. This would then result in the inverse sine of u over a. And that's being evaluated, since it's a definite integral, at 1 and 0. So this is the inverse sine of 1/2 minus the inverse sine of 0 over 2, or 0. The inverse sine of 1/2. Now, sine has a domain restriction of the quadrants 4 and 1. And since I have a positive sign that I'm looking for what angle provides a sine of positive 1/2, this has to be in the first quadrant. That'd be pi over 6. And right here, again, I'm limited to the fourth quadrant and the first quadrant. Where is sine equal to 0? At what angle? That's at the angle 0. So this would be pi over 6. Number 10, at first glance, doesn't match any of our formulas. However, we could complete the square on the denominator to make this match the inverse tangent formula. On that denominator, I'm going to go through and remind you of how you complete the square. When you complete the square, what you do is you're going to kind of group together the first two terms. This would be a and b. You take the value of b, you cut it in half, and you square it. So 2 divided by 2 is 1. 1 squared is 1. That's what I'm going to both add and subtract from that denominator to keep this equation balanced. Now, what I have now is I have a trinomial that can be perfectly factored. It's a perfect square. This would be x plus 1 times x plus 1, or x plus 1 quantity squared. 2 minus 1 is 1. Now, this is a match For the inverse tangent, you might feel like, I like it to have the a squared in the front. Totally up to you. If you would prefer to rewrite that to identify that easier, that's up to you. A is the square root of 1, which is 1. X is the square root u is the square root of the function squared, so x plus 1. And du is dx. So if I do a quick rewrite, this would be the integral of 1 over a squared plus u squared, and dx would be directly replaced with du. This is a perfect match for inverse tangent. So the answer would be 1 over a times the inverse tangent of u over a plus c. Well, in this case, a is just 1, so I don't need to write a constant multiplier in the front. And u is x plus 1 divided by 1 would be the inverse tangent of x plus 1 plus c. And that is the end of our notes for this lesson.